Warning: Oleum, or fuming sulfuric acid, is extremely corrosive. Wear gloves and protective clothing when handling it. The fumes are corrosive and possibly carcinogenic. This experiment must be performed outside or in a fume hood. This experiment also handles high-temperature corrosive molten salts. Containment and damage mitigation protocols must be in place. This experiment should only be performed by an experienced chemist. Greetings, fellow nerds! Another Lab Notes video on making oleum. This time I got up to about 20 to 25% yield, so I'm doing better, but still not quite at the 30% minimum I would consider amateur viable. Especially for something this dangerous. You don't want to spend too much time making it over and over again, as that raises the chances of an accident. So to recap, I'm making sulfur trioxide and the associated substance oleum, or fuming sulfuric acid, which is just regular sulfuric acid with added sulfur trioxide. It's like sulfuric acid's angry gangster cousin. I'm going to do this by the modified pyrosulfate method, where I heat sodium bisulfate until it pyrolyzes into sodium pyrosulfate, and then add sulfuric acid to boil out the sulfur trioxide. So far the yield is about 13%. Since this is a Lab Notes video, I'm not going to explain all the context or scientific points, and I won't be doing much safety analysis. I'm just reporting on my research so far. To know the full context, watch my videos on distilling sulfuric acid, and the previous Lab Notes video on making oleum. Links are in the video description. But basically, I'm trying to improve on existing amateur methods which are more dangerous or more expensive. I'm trying to find a cheaper and safer approach, even if not necessarily as high yielding. So what did I do differently this time to get 20 to 25%? As usual, I started by heating the same quantity of 400 grams of sodium bisulfate, or about 3 moles, on a ceramic hot plate in a 1 liter flask with a distillation adapter and condenser. I found that the product was much cleaner if I first set up everything as usual, but added 75 grams or so of sulfuric acid and then did the pyrolysis step. By itself, this did not improve yield, but the boiling sulfuric acid decomposed any lingering residues or greases in my apparatus and any dyes in the PTFE tape I used to seal the joints. The overall result is that I had less contamination of the sulfur trioxide product later. So I think I'm going to add a sulfuric acid pre-cleaning step to my oleum synthesis procedure. Anyway, I proceeded to distill the acid and push the temperature to maximum to pyrolyze the sodium bisulfate. This produced sodium pyrosulfate. Then I push it further by wrapping more and more foil insulation around the flask to distill off more and more water. I kept wrapping until no more liquid distilled over, indicating we've reached the maximum temperature for this particular setup. Something to note is that fuming never occurred during the pyrolysis, so this step is not hot enough to pyrolyze further and produce sulfur trioxide directly. Alternatively, I might be releasing a little, but it's mixed in with the water coming over and thus distills as sulfuric acid. Anyway, once I stopped distilling, I turned off the power and let it cool. And here is the insulated flask. As you can see, it needs a lot of insulation. If you can use furnace wool or glass wool insulation, then by all means do so. I think wool would be better, but I personally don't like using it because all of my wool sheds glass particles. Anyway, I waited about 2 hours for it to cool and then added 200 grams of concentrated 98% distilled sulfuric acid through the top. I'm adding it this way so I don't have to remove the insulation. I also found the mixture to be reasonably well behaved during distillation, so I didn't put in a stir bar this time. So now I change out the receiver and start gently ramping the temperature. Let me change the lighting and the camera angles so it looks a little cleaner. And there we go. I started at 200 Celsius at first, and then raised it to 300 Celsius after half an hour, and held it for another half an hour. Then I raised the temperature 10 degrees every 10 minutes until I noticed it was fuming at about 360 Celsius. The better insulation meant the reaction started at a much lower hot plate temperature. Previously, I needed 490 degrees Celsius. Since it's a lot cleaner this time, I didn't have to discard the first few drops of sulfur trioxide. Interestingly, the sulfur trioxide that first condenses is the gamma form, which is liquid at the 21 degrees my lab is. But it polymerizes into the beta and alpha forms, which are solid. And you can see the polymerization happening at the end of the condenser here. You can also see the pool of sulfur trioxide at the bottom starting to polymerize as well as it cools. In this run, I produced enough sulfur trioxide that it actually solidified and blocked the condenser. This is a known problem with sulfur trioxide preparation, and I'm actually glad it happened here since it means I'm on the right track. The usual way to remove it is to heat it so it melts. I'm using a torch to gently heat the outside of the flask. Granted, this is not very effective since we're heating the outside, and we need to warm up the air inside the flask to the point that the sulfur trioxide melts. An extremely inefficient process. But I didn't want to heat the sulfur trioxide directly for safety reasons. If you're doing this, I actually don't recommend a torch, but use a heat gun. A torch has a much higher risk of cracking the glass. And there we go. It took several minutes, but it's down. And after that, I continued the distillation to get some more sulfur trioxide. Interestingly, the solidified sulfur trioxide did not reform after melting it. While the sulfur trioxide in the pool at the bottom is resolidifying, the condenser is not. The liquid of gamma sulfur trioxide needs some sort of initiator to begin polymerization. Since I melted off the solid plug of sulfur trioxide, I converted all of the polymers into the gamma form and now they can't polymerize again. This would be a good thing to prevent clogging of the condenser, but now without seeing the solid, I don't know if we're distilling sulfur trioxide or if we're distilling sulfuric acid. And looking at the pool at the bottom isn't useful since it solidifies too slowly. So I'm going to try and force the initiation of polymerization by taking advantage of the fact that trace water will initiate it. Let me just slip off the receiver, and that massive plume of fumes is sulfur trioxide reacting with the water in the air to make sulfuric acid mist. I'm using this pipette to smear some of the dripping sulfur trioxide and expose it to the moisture of the air. The moisture alone is enough to initiate polymerization, and it might be hard to see on camera, but you can see solid sulfur trioxide is already forming on the pipette. Anyway, I'm going to smear the solid sulfur trioxide back onto the condenser tip. If I can get some of it to stick, then it will serve as the seed crystals to initiate further polymerization of the sulfur trioxide. Let me put the receiver back, and it seems to be working. We're solidifying more sulfur trioxide. At least this confirms we're still distilling sulfur trioxide. I'm still trying to figure out a way to know when we're switching from sulfur trioxide to sulfuric acid, but watching for solidification and then dissolving when it switches still seems to be my best option so far. Another option might also be the intense fuming of the pipette earlier as a loose indicator that we have the sulfur trioxide. Sulfuric acid does not fume this much, so if we had no fuming, we'd be fairly certain we were no longer distilling sulfur trioxide. The problem is that we have to open the receiver to run the test, and we'd have to do that multiple times during a run. So that's not exactly a good option, but it's something to keep in mind. And it looks like it's getting too big and about to clog again. So I'm going to see if I can melt the clog by turning off the cooling. And it looks like the clog isn't growing much, but it's not melting even after half an hour. And I don't want the temperature to rise too much, so I'm going to turn the cooling back on and try physical removal this time. I'm taking off the receiver and trying to push off the sulfur trioxide with the pipette. Okay, I can see why this is not the recommended way of removing it, and why all references recommend heating. This sulfur trioxide is actually pretty hard, like wax. Okay, I got it down, but I'm not doing that again. I needed to apply some decent force. I don't like the safety risk of that because if it needs too much force, then there is a risk it can fling off when it breaks and land somewhere we don't want it, like on us. Alternatively, we may accidentally tip over our apparatus or unseat a seal. I'll go back to the heating method despite being less efficient. It just feels safer than poking at spicy flesh-eating wax. And as we continue distilling, the sulfur trioxide is solidifying again, thankfully. And it looks like it's shrinking now, which means we're distilling sulfuric acid that's dissolving the sulfur trioxide. I did a quick fume test of the liquid, but it still seemed to fume a lot, so that alone is not enough to test whether we're distilling sulfuric acid or not. But it seems like we're done, so I'm going to change out the receiver and stopper this one with a glass stopper wrapped with PTFE tape. At this point, I'm going to fume test the distillate again, and it's definitely fuming a lot less now, and also it's not solidifying. If this were sulfur trioxide, I'd expect it to solidify on air at first before dissolving again as it absorbed more water. But this distillate is remaining liquid, so I'm pretty sure it's sulfuric acid, and we're done with the sulfur trioxide distillation now. So it does seem the fume test can be used to find distillation endpoint if we also look for sulfur trioxide solidification. So I learned something new, and that's why I'm doing these experiments. To learn how to work this new sulfur trioxide synthesis process. I'm just as much of an inexperienced noob as you guys are in this regard. Let me test that one more time. It'd be pretty stupid if it starts solidifying again after I just said that. But it looks like it's confirmed no more sulfur trioxide, just sulfuric acid now. So now we turn the heating to maximum and regenerate the sodium bisulfate by distilling off the sulfuric acid in water. This is what I love about this process. It's essentially catalytic and overall separates sulfuric acid into sulfur trioxide and water. So I don't need very high yields, since everything can be recycled. This dilute sulfuric acid was saved to be repurified. Okay, once the pyrosulfate was regenerated, I wanted to run a second trial, so I once again added 200 grams of concentrate sulfuric acid. Not the sulfuric acid I just distilled a minute ago, but a fresh quantity with the water removed. And once again, I carefully raised the temperature until it fumed, and readjusted to get a slow, steady drip rate. I'm doing this to see if all the events like freezing, melting, and fuming all happen consistently. Amateurs love their reproducibility and robustness, perhaps even more so than professionals. And indeed, it looks like we're getting sulfur trioxide solidification just like before. Except this time it's a little more crystalline. And it fell off, but at least it reforms, and again it gets big enough to clog the condenser. Learning my lesson this time, I melt it down with heating rather than attempt to push it down. And once again, the melting seems to clear off any seed phase of sulfur trioxide, so future polymerization is stopped. This is good to know if I want to stop clogging. But for now, the polymerization itself still seems like the only way I have to track the transition to sulfuric acid distillation. So I'm going to try my reseeding procedure of simply exposing a few drops with pipette to ambient moisture, and then smearing it back on the condenser tube. Just exposing the condenser alone doesn't seem to be all that consistent. Maybe the seeds of sulfur trioxide polymer need to be anchored to the glass. Just exposing it to air briefly doesn't give enough time to anchor before it gets washed off again by more distillate. And there it goes. At this point, if you're still with me, I'd like to ask you to comment and like this video so the YouTube algorithm knows I exist. And maybe subscribe if you like to keep up with this project. I also have a Patreon if you're interested. Anyway, after another half hour, it's starting to shrink again, indicating the distillation is transitioning to sulfuric acid. So I changed out the receiver, and since the solid sulfur trioxide is pretty small, it seems a lot easier to push off with my pipette. I also did the fume and solidification test again, where I held a drop on my pipette to see if it would solidify. And again, it remained liquid, indicating we're transitioning to sulfuric acid. And fuming seems to be minimal. So the test does seem to work, but admittedly it's not the best test. It's a little dangerous to be waving around a highly corrosive liquid, but at least it's better than no test. So here are the 2 runs of Oleum. They're remaining solid now, so the purity is much higher, and after titration I got somewhere above 80%. The mass collected was about 30 to 35 grams for an effective yield of about 24 grams to 28 grams of sulfur trioxide, or 20 to 25%. So not quite at my goal of above 30% yet. I did another trial, but instead of gently raising the temperature during distillation, I tried blasting through it on full heating. But it seems temperature control is much more important than usual. If heated too high too fast, we get severely reduced yield. I think at high temperature, the sodium bisulfate produced itself starts to pyrolyze and release water, reducing yield. So maybe the insulation and higher temperature during the pyrolysis step isn't what's increasing the yield, but the insulation allows me to be very precise and gentle with the heating in the distillation step. I'm not exactly sure, that's just a hypothesis. This could simply be a bad run. We'll need a lot more testing, and that's why I'm making these lab notes. Anyway, another test I did was instead of just 200 grams of acid, I used 400 grams. I just wanted to see if there might be an equilibrium effect where adding more acid makes the sodium pyrosulfate react more and release the sulfur trioxide sooner. But instead the yield got reduced, so I think adding more has no effect on the equilibrium. And the reduced yield came from the fact that the extra sulfuric acid also has 2% or so of water, which itself reacts away what meager sulfur trioxide is produced. So that's good to know. Maybe I should go with 100 grams of acid next time and test a small amount, since we're not getting high enough yield anyway to warrant 200 grams of sulfuric acid. Unfortunately, I hit a snag. The ceramic hot plate failed. It no longer accepts control inputs. Not going to lie, this bothered me a lot since this hot plate was a gift and I barely used it before damaging it. I guess no hot plate stirrer survives contact with me. Fortunately, I do have other ceramic hot plates and we've already established that we don't need stirring for both the pyrolysis and the distillation steps. So a much cheaper non-stirring hot plate can be used. But before I do that, I'm going to take apart and analyze my broken hot plate stirrer to see why it failed. I don't want the same failure to happen to my next ceramic hot plate if indeed I was the cause. So that was my lab notes video on Oleum production. We're up to 20% or so, and we've learned more of the idiosyncrasies like how it solidifies and polymerizes, and we've come up with some new techniques like using a pipette to induce polymerization by seeding it with moisture from the air. Hopefully I can figure out this ceramic hot plate issue, and then we can do more research. Thanks for watching. And special thanks to my Patreon members for supporting my channel. I really appreciate it.